Hi, my name is Nikhil and I'll be talking about our paper on Lifecycle by Capsule Networks for spatio-temporal analysis of facial actions. Let's get started. Facial action coding system, as proposed by Ekman et al., provides an objective evaluation of human facial expressions by encoding facial muscle activity in terms of their contractions and relaxations. Thus, the facial expressions can be encoded precisely to depict which part of the face moved and how, without needing any subjective interpretations. Action unit activation patterns follow a temporal evolution, here referred to as the AU life cycle. Starting from a resting phase, the facial muscle starts to contract during the onset phase until they are completely contracted, depicting the apex of an expression. At this stage, the highest intensity is expressed, with the individual holding the expression for some time. This is followed by the relaxation of muscles during the offset phase before returning back to the resting phase. Existing approaches examining action unit activation patterns can largely be divided into two categories: those that focus on spatial features and those that consider spatio-temporal features to determine action unit activations. While spatial features capture local relationships between different face regions, spatio-temporal features focus on how these features vary across time. Spatial features also focus on hierarchical dependencies between local regions, while spatio-temporal features are sensitive to variations over time. Spatial features can be particularly useful during peak intensity frames, such as apex frames, where low variations are experienced in contiguous frames. On the contrary, during onset and offset phases, where high variation is experienced, spatial temporal features may provide more descriptive features. Thus, both spatial and spatial temporal features help improve model performance depending on the AU life cycle. So in this work, we examine whether we can dynamically learn when to focus on spatial or spatio-temporal features depending on where in the AU life cycle the frames originate from. For this, we look at capsule networks for inspiration. The capsule networks, as proposed originally by Savor et al., focus on encoding local spatial relationships as feature primitives for the object of interest. Each learned feature primitive is represented by its length, encoding the probability of occurrence for that particular object, as well as other encoded features such as pose, orientation, size, etc. These capsules are learned. These capsules are able to learn local spatial relationships between the object of interest and its surroundings. For example, in the image shown here, each capsule encodes feature primitives in terms of the triangle and the rectangle constituting the image of a boat, as shown here. Each position on the image here highlights at each position in the image here, the length of the vector represents the probability of occurrence of this particular primitive here, whereas the orientation represents its pose. When applied to faces, this means that each capsule may learn different facial features relevant to different parts of the face, encoding their position as well as pose among other features, as well as capturing local relationships between these particular features. Contiguous frames can be examined similarly to evaluate how these local relationships vary across time, providing a spatial-temporal understanding of these features. Thus, for simultaneously learning spatial and spatio-temporal facial features, we propose the AULA-Caps network that consists of two channels of processing. For each frame, we take two frames immediately preceding and succeeding it, forming a temporal window of contiguous frames. The frame of interest, here the central frame, is passed to the spatial stream, consisting of two residual blocks, followed by a primary capsule layer extracting spatial features. Simultaneously, the entire window is passed through a spatio-temporal stream consisting of several 3D convolution layers, followed by a 3D capsule layer that extracts spatio-temporal feature primitives. The primary capsules from both the streams are concatenated together and routed such that each individual capsule is comparatively weighted based on their contribution towards predicting the 12 action units. The length of each of these AU capsules represent the probability of their activation in the frame of interest. A weighted margin loss is used as the objective for training the model for AU prediction. Additionally, the AU capsules are also passed to the decoder model that learns to reconstruct the frame of interest. A mean square error based loss is used as an objective for this, further regulating learning in the model. We evaluate the proposed approach in several ways. First and foremost, we evaluate the model's ability to predict the action units, testing on two data sets, the BP4D and the GFT dataset. The BP4D represents simpler settings by providing face-centered images recorded in lab settings, where the participant data is recorded under different illumination and pose variations. The GFT, on the other hand, is recorded in group interaction settings, where participants are sitting together and tasting drinks while talking to each other, resulting in frames with high level of occlusions, as well as a naturalistic environment for the interaction. We also evaluate the model by conducting several ablations on it, examining how, for example, how spatial and spatio-temporal features contribute to model performance, how capsule-based computations improve over convolutional-based networks, and finally, how different window sizes impact model performance. We also visualize learning in the model in terms of the decoder's ability to reconstruct the frame of interest, as well as visualizing saliency maps depicting where the model looks at while predicting the output. When looking at the results, first for the BP4D dataset, we achieve state-of-the-art results, outperforming other recent approaches. However, for some action units, for example AU4, the CNN-LSTM model performs the best, while our approach does not perform that well. This could be due to the fact that the AU4 samples are much less in number compared to the other datasets, resulting in an imbalance in the distribution. While even for the samples that do exist, they are co-occurring with AU7, 10, and 14, resulting in confusion in the model for this particular one. Nonetheless, our proposed approach outperforms other methods on overall F1 scores. The GFT data story is a bit different due to the increased complexity of the dataset, due to frame drops and occlusions. The overall results of all the approaches are much lower. Despite that, our approach achieves the second best overall results, with the nearest approaches either evaluating only 10 action units or evaluating on a subset of the data of the subjects. However, we see that our approach underperforms for certain AUs such as AU1, 4, and 14, where the best approach is way ahead of us. Again, this could be due to the imbalances in the dataset, as can be seen here, as well as a lot of frames being dropped, resulting in the spatio-temporal features not being so interfering with the spatio-temporal features being learned. To understand the model better, we perform several ablations, as I said, on the model. We see that the spatial features individually perform better than spatio-temporal features on frame-based analysis, although combining both these feature sets improve model performance. Similarly, capsule-based computations achieve better results than simple convolutional networks, while also decreasing the number of parameters to be trained. Finally, ablating with respect to window sizes, in general, the model performance increases when longer windows are used. However, window size of 5 performs the best. Now, also looking at how the model is able to dynamically weight spatial and spatio-temporal features, we see the individual contributions of these features towards model performance. So for similar contiguous frames, spatial features dominate, while for regions where where the model goes from where the image goes from low activity to high activity, or vice versa, we see the spatio-temporal features dominating the model predictions. Finally, while visualizing learning in the model, we witness that the decoder is able to reconstruct the frame of interest quite well, capturing the action units as well as the identity of the individual. Yet for a few cases, the ones highlighted, we see that although the model is able to capture the action unit being expressed, the identity of the model, as well as the race and gender, is lost, which may be due to the fact of due to the lower number of samples for this particular subject in the dataset. While visualizing saliency maps for different AUs, we see that the model is able to focus on relevant parts of the face, resulting in improved model predictions. Yet for some action units, for example here in AU4, we see that the model is a bit confused. It looks at other regions of the face as well, which are not as relevant. Again, this could be due to the lower number of samples for AU4, as well as the co-occurrence patterns confusing the model in terms of where to look at. To conclude, we present the first approach, combining spatial and spatio-temporal capsule-based computations for AU prediction. We witness that adding spatio-temporal features along with spatial information greatly improves model performance by providing context, and also selectively learning to focus on spatial or spatio-temporal features enables a robust performance of the model. Yet we do see that the model is sensitive to the size of the sequence window being examined, and in future we'd like to examine if we can use dynamically adapting window sizes based on which AU we're looking at, and also using, for example, the anchor frames, which look at against which we can measure the activity of the action units. We would also like to examine the data imbalance problem and look at approaches such as looking at co-occurrence patterns, where we know that if one AU is present, the likelihood of the other AU being present is also high, which might improve model performance, and also looking at advanced methods such as synthetic instance generation to balance out data sets, and also continue learning to learn with dynamically changing data sets and data shifts. Finally, I'd like to thank my other co-authors for their contributions to this work, as well as our sponsors. Thank you so much for listening.